Hello guys, you're welcome to Edumatop, and this is a quick video on photoelectric emission for physics, copied right from the JAMB syllabus. Okay, once you can finish this, okay, you are sure of getting any question that comes out from this particular topic. So this is photoelectric emission. So let's jump right into the video real quick. Now, photo is from the word light. Okay, when you see photo, it means light, and electric has to do with movement of charges. So the definition of photoelectric emission, okay, has to do with the emission of electrons from the surface of a material or a metal when light falls on it. Okay, so you can see the definition on the screen. It is the emission or liberation of electrons from the surface of a metal when light falls on it. So the name is photoelectric emission. So emission has to do with the ejection of electrons from the surface of a metal. And you can see this diagram right here. Okay, you can see light. This three lines here. These three parallel lines are the incident rays. Okay, it could be ultraviolet rays. Okay, or heat coming from light hitting a metal. This blue line is the metal, and you can see electrons that have been ejected from the surface of the metal. It is this incident light that causes the ejection of these electrons. When the incident light reaches a particular frequency, it will cause the electrons to be ejected from the surface of this metal. You can see it's very, very straightforward. It is just light causing ejection of electrons from the surface of a metal. There are some points that you have to remember when you're talking about photoelectric emission. So the first thing is a photon. A photon. A photon is just a particle of light. Okay, so it's a particle representing a quantum of light. Okay, and a photon carries energy. Okay, each unit of light particle is called a photon, and each photon carries energy. And the energy of a photon is given by this formula, E equals to HF. You can see it right here. E equals to HF. E equals to HF. E is the energy. H is the Planck's constant. The Planck's constant has a value which is 6.626 times 10 to the minus 34 joule seconds. Okay, so that's the Planck's constant. Very, very simple. It's very simple. So E is equals to HF is the energy of a photon. And don't forget that from your wave, you know that the speed of light c equals f lambda. Okay, c equals f lambda, and from there, if you make f the formula, you see that f will be equal to c over lambda. So the formula for energy of a photon is E equals to hf, or you can say E is equals to hc over lambda, where c is the speed of light, okay, and E is the energy of the photon, lambda is the wavelength. Okay, very, very simple. Okay, now let's move on to another thing, which is the photoelectron. Now, what are photoelectrons? Photoelectrons are just the electrons that have been ejected from the surface of the metal. Okay, the electrons that have moved away. For example, look at this electron here, E. Okay, this electron, once it gets ejected from this metal, once it leaves the surface of this metal, it becomes a photoelectron. But if it is inside the metal, it's just a normal electron. But once it gets outside the metal, it becomes a photoelectron. So a photoelectron is just an electron that has been ejected from the surface of a metal when light has fallen on it, okay, or when light is incident on it. And this electron has the ability to move around. It can move around based on the kinetic energy that it possesses. So it can jump around. Okay, so that's that. Then let's move to the threshold frequency. Now, threshold frequency is defined as the minimum frequency which an incident light must attain before it could eject electrons from a metal surface. Okay, so each incident light, this light that you're seeing here, this parallel rays, once it hits this metal, this light must have a sufficient frequency. Okay, that frequency is called the threshold frequency. Once the energy, once the frequency of the light reaches that particular frequency, it will cause the electrons to be ejected from the surface of the metal. But if the light is not up to that frequency, it will not cause the electrons to be ejected. Just as if you are hitting something, you have to overcome the energy that is holding that thing down before that object can move. So this light rays, the frequency has to build up to a particular frequency where the frequency of the electrons, the energy holding the electrons will be broken down. If the energy holding the electrons have been broken down, then the electrons can be ejected or they can move away from the metal. That is why this light energy must reach that frequency, and that frequency is called the threshold frequency. Okay, if the energy of the light is not up to that frequency, nothing will happen. Then let's go to the work function. The work function is just the minimum energy that is required to eject electrons from the surface of the metal. Okay, just the minimum energy, the minimum amount of energy that is required to eject the electrons from the metal. Take for example, if this metal here has a work function or a minimum energy on, let me say, of 30 joules, then this light that is falling on it must reach 30 joules before it can eject electrons from this metal. If this metal has 30 joules and this light here, the incident light, the energy of the light is like 20 joules, then nothing will happen. The electrons will still be embedded inside the metal. But once this energy of the light gets to 30 joules, then it will cause the electrons to be emitted. Electrons will leave, or they will be liberated from the surface of the metal. So the work function is just the energy that must be overcome. Okay, it must be overcome. If it's not overcome, then the electrons will still remain inside the metal. So that's about work function. Okay, and it's also defined as the work that must be done against the barrier. Like I said just now, it is the energy that is holding the electrons down. So the energy of the light must break down, or it must defeat the energy of the work function before the electrons can be moved away from the surface of the barrier. Okay, so this is just the breakdown for the basic thing that you need to know for work function, photon, photoelectrons, and definition of photoelectric emission. Let's move to the next part now. Now, for this next part, we're going to talk about the work function. You can see the symbol. The symbol is phi. This is the symbol of the work function here. This is the symbol of the work function. The symbol is phi. And phi is HF naught. F naught is the threshold frequency. Okay, or you can see the fundamental frequency. So F naught is equals to Fc over lambda naught. Lambda naught is also the threshold wavelength. Okay, so once energy is broken down, once energy is overcome, then the electrons will leave the surface of the material or the metal. So the incident light must be greater than this energy, or must be equal to it, before the electrons can be defeated, or before the electrons can be ejected from the surface of the material. Okay, now please take note of this formula, very important. Now we'll move to photoelectric equation. This equation is also called the Albert Einstein equation. Okay, so don't forget that each incident energy, the energy that is falling on the surface of the metal, has a particular energy. The energy is HF, like we have discussed just now. Okay, now once this energy is equal to the energy of the work function, then electrons will be emitted. Okay, now you can see this formula here. Now if this energy, you can see from this diagram, let me just bring this back. Let me bring this back so you can understand it better. Once this energy of the electrons here, this energy here, this electron is falling here. Once this energy is greater than the energy of the work function, then the electrons will be emitted, like I said earlier. But if this energy is very, very high, as in the magnitude of this energy is a multitude of times greater than the work function, then the electrons will keep on moving with a kinetic energy. That kinetic energy is given by this formula. So E minus the work function. This E here is the energy of the incident light that is falling on the metal. Okay, while this energy, this phi, is the work function, the energy that is holding the electrons down. So once energy of the light, incident light, is greater than the energy of the work function, then the electrons will now move away from the metal, and they will keep on moving with this kinetic energy. So the energy that the electrons will use to move after they leave the surface of the metal will be given by E equals to E minus phi, where phi is the work function, that is the energy holding the electrons down. So this equation is called the Albert Einstein photoelectric equation. Okay, very, very important. Okay, Ke is equals to E minus phi. And note that the number of electrons emitted depends on the intensity of the incident light. Now, how many electrons will be emitted from the metal when light falls on it? You cannot know how many, but the number that will be emitted depends on the energy of the light, the strength or the intensity of that light on a particular unit area. Okay, that's about the number of electrons emitted. It depends on the intensity of the incident light. Then the kinetic energy of the electrons, the photoelectrons, that will be emitted from the surface of the material. That kinetic energy depends on the frequency of the incident light. It doesn't depend on the intensity of the light. It depends on the frequency. And you know that frequency also depends on wavelength. So the kinetic energy of the photoelectron depends on the frequency or the wavelength of the incident light. Take note of that, very important, and try to remember this formula. Ke is equals to E minus phi. E is the energy of the incident light. Phi is the work function, which is the energy that is holding the electrons down. Then Ke is the recipient energy, the remaining energy when you subtract E minus the work function. Okay, so now we move very quick to the next part, which is this photocell. What goes on here is look at this box here. This box is a UV source. A UV source is an ultraviolet source. Okay, So it brings out light, okay, of a particular energy. And we have this diagram here. You have an anode and the cathode. The cathode is the negative pole, while the anode is the positive pole. So once this light falls on this metal, you can see these red lines here. These red lines are the light energy falling on the surface of this metal. So once the light falls on the surface of this metal, once it gets to a particular frequency called the threshold frequency, it will cause the electrons in this cathode to be ejected. Now, once these electrons are ejected, they move, and you plug this side to a light source. These electrons will now move. They'll start moving towards the cathode. Positive and negative poles attract each other. So this is positive pole, negative pole. They'll be attracted. The electrons will move in this direction. So once they move to the positive pole, they become attracted, and the movement of charges gives you what is called current. Current is the movement or flow of charge per unit time. The rate of flow of charge will give you current. So once you have electrons flowing, you have current. So this photocell works in the sense when it works in the phenomenon that it works on the basis that once light falls on this guy, yeah, this cathode, electrons will be ejected. This terminal here will cause a PD to flow in this direction. That PD will move these electrons towards the anode, which is the positive pole. And the movement of that electrons constitutes what is called a current. Once electrons are moving, you have what is called current. Okay, so these are the ejected electrons here. These are the terminals that will be plugged to a source, an electric source. This is the cathode, this is the anode. This place is a vacuum. Then this is a UV source. Okay, so that's the basics. That's how it works. That's the basis of the photocell. And the movement of these electrons will give you a source of light that you can use for anything you want to charge, or maybe to lighten up your room or whatever. This concept is applicable in what is called like your fluorescents that you have at home. This is the concept. This is how it works. Then you also have what is called the application of photoelectric effect. Let's call the application, how it can be applied. It can be applied in burglar alarms. You can use it in burglar alarms. You can use it for automatic doors. You have it in photometers, television cameras, solar cell, and fire alarms. Okay, so these are the applications of photoelectric effect. Very, very simple. Now, let's move to what is called the stopping potential. Stopping potential. It is just the potential that is trying to stop the electrons from moving towards the anode. Okay, let me bring this back here. If you look at this, I told you guys that once this light falls on this guy, electrons will be ejected towards this anode. So as the electrons are moving, there's a potential that can prevent these electrons from moving forward. That potential will be acting downwards like this. The electrons are moving like this. The negative potential or the stopping potential will act downward to stop the electrons from moving towards the anode. So that potential that stops the electrons from moving towards the anode is what is called the stopping potential. Okay, so this is the definition here. You can see it right here. It can be defined as the potential difference of the anode of a photocell with respect to the cathode, beyond which no electron will reach the anode. Okay, so this is the anode, this is the cathode here. So it is just the potential, or the PD, that prevents the electrons from flowing from the cathode to the anode. And it is related to the energy of the electrons. Or let me say, it's related to the kinetic energy of the electrons. Because the kinetic energy of electrons will depend on the stopping potential, and it's given by this formula. Ke is equals to EVS. Now, EVS, E is the electronic charge. Okay, I know that the formula for K, kinetic energy, is half mv squared, where m is the mass of the electron, v is the velocity of the fastest electron, E is the electronic charge, and Vs is the stopping potential. So the symbol of stopping potential, the symbol is Vs. Then m is the mass, Ke is half mv squared. So we have this diagram here which can tell you how the stopping potential varies. Now let's look at how kinetic energy varies. You can see this graph here. You have kinetic energy. This F naught is the fundamental, or you can say the threshold frequency. So when you start hitting this material, like when you start hitting the metal, the energy of this material will begin at this interpolation here. You can see this interpolation, which is W naught. As you're hitting the material with the incident light, the energy will be rising. The energy will continue to rise until it gets to F naught. Once it gets to F naught, then you can have what is called kinetic energy. Kinetic energy start moving upwards. So the fundamental frequency and the kinetic energy are related with like in direct proportion. So as fundamental frequency increases, kinetic energy also increases. But nothing happens when you hit this. You can see this dashed line here. You have to overcome this W naught here, or the work function. It is the energy that is holding the electrons down. So you have to heat it up. You have to use the energy of the incident light to heat the metal up for a long time until you get to this point here. From this point here, you cannot have what is called the ejection of electrons. So this energy must be overcome first before you can have the electrons moving like this. So work function and threshold frequency also they're also related the same way. This from the threshold frequency, then from this point the work function has been defeated. So from here you can have ejection of electrons moving in this direction. So the energy keeps rising in this direction. The same way the energy of the kinetic energy of the electrons keeps rising in this direction once the work function has been defeated. Okay, so this is just the basics for photoelectric emission. Okay, so as you can see, the topic is very simple. If there's any question you have, let me know in the comment section. Now let's move to past questions and let's see what JAMB has been dropping for several years on this topic. So that's the end of the tutorial part for this topic. Please, if you have any question, let me know in the comment section. Then let's go to the past questions now.